Hello everyone. So that cute thing you see in the picture on the right is a Turing machine, what we've been studying for a little bit with its tape and the head moving across it and so forth, primitive looking thing. And on the left is a supercomputer. Church's thesis is going to tell us that these are kind of the same. Well, they sure don't look the same, so we'll have to see in what sense that sameness is true. And we'll also study something called universal Turing machines, which effectively show that you can write software for Turing machines. Okay, let's go. So the Turing machines we introduced in the last couple of lectures are very simple objects. One of their merits is that they can be described very precisely in a mathematical way. A Turing machine formally is a 7-tuple whose constituents are sets, functions, and elements of these sets. So it's a very mathematical object. This simplicity and the ability to cast it mathematically is valuable in our context, because a lot of the time what we want to do is study and ask questions about programs. We want to reason about whether programs halt or not, whether one type of program can be converted to another type, and so forth. So the simpler our model of the program, or the simpler our programming language, the easier it is to state and study and answer questions like that. A modern programming language can be turned into a mathematical object. It does have a semantics that permits that, but it would be an extremely complicated object, and we are getting around that. But we pay a price for this simplicity, which is that we also want to actually write programs, and the more low level is our programming language, the more tedious it is to write programs. In fact, as we already saw, even giving programs to decide quite simple languages is quite difficult if we're working in the language of Turing machines, even though in a high-level programming language it might be quite simple. Church's thesis is what enables us to bridge this gap. What it says is that Turing machines are effectively as powerful as modern-day computers. So this tells us that when we want to write code, we can write that code in a high-level language like Python or C# or whatever is your favorite language, and appeal to Church's thesis to say, yes, you could turn that into a Turing machine. We're not actually going to do that because it would be awfully tedious, but we know that in principle it's possible. Church's thesis underlies a lot of the meaningfulness of what we do here, beyond just giving us the ability to write our programs in a very high-level way. We will be making statements about Turing machines of the form, the halting problem defined as given a Turing machine and an input, does the Turing machine halt on that input, is undecidable. This would not be terribly interesting if it was only about Turing machines, but Church's thesis says that a consequence of this is that it's impossible to write a C# program that can take input a Python program and an input for the latter and say if it halts or not. So the conclusions we draw apply to modern computing because of Church's thesis. So right now I said that Turing machines are as powerful as modern-day computers. So let's sort of elaborate a little bit as to what that might mean. We would be looking actually at a theorem, a formal theorem, but it says is that if I give you a program P in the C programming language, using C as an example, it's possible to build a Turing machine M such that the original C program on my Turing machine are functionally equivalent. So they're the same in the following way. Functionally equivalent means that on any input, these two programs do the same thing. Remember, programs take inputs, and on these inputs, they can have many possible actions. They can accept or reject, in both of which cases they halt. They can loop, which means they run forever. They might, if they want, have an output, and so forth. Functionally equivalent means all these things are preserved. If our C program accepted with an output 0, 1, 0, our Turing machine will also accept with an output 0, 1, 0. If our C program ran forever, our Turing machine would also run forever, and so forth. So what that means is anywhere you're using the C program, you could just substitute the Turing machine. Now, as a warning, we are certainly not going to preserve running time, so the Turing machine will be way slower. This is an in-principle statement. Alonzo Church, who's credited with this thesis, according to this Wikipedia article, I should actually be calling it the Church-Turing thesis, was born in the early part of the 20th century. He passed away in the mid-90s. He got his PhD from Princeton. Of course, back then, his PhD was in mathematics. There was no computer science around. He was a logician, like many of the people who originally conceived of and studied computability theory. And he has many big, interesting results to his name. For example, that the undecidability of piano arithmetic. He invented something called the lambda calculus, which is effectively equivalent to Turing machines and thus equivalent to modern day computers as well. So let's try to justify as best we can this claim, which is effectively Church's thesis. I'm given a C program, call it P. I want to build a Turing machine such that this Turing machine M and the program P are functionally equivalent. So they do exactly the same things on all inputs in terms of accept, reject, halt, or not halt, and what they output. So how could we go about establishing this? Well, if you think about programs that you yourself write, or that most people write, they're written for some purpose. I might write a program for solving the reachability problem on graphs. If that's the case, I might ask myself that in order to establish this statement for that program, I should show that I can write a Turing machine to solve the reachability problem on graphs. You could try to approach it this way, but there are many reasons why this is not going to work so well to establish the statement that we want. First of all, these steps are rather hard. Maybe you know what problem a program you write is solving, or even a program that's kind of out there is usually accompanied by some description of what it's trying to do. But we're talking about completely arbitrary programs. If you're handed some arbitrary program, it's not at all clear how you would figure out what problem it's trying to solve. That type of program analysis is pretty infeasible. So any attempt to need to know the semantics of your program is going to be kind of doomed failure. Secondly, if every time you give me a program, I'm going to have to write a new Turing machine by figuring out what the program does in some intrusive way and mimicking it, I'm going to have a lot of Turing machine programming to do, and that's also quite a pain given how hard Turing machines are to program. So we'll use another approach. Now, one of the general themes that we'll see in this class that we will illustrate here and also later is that historically this area grew in mathematics, and they conceived many ideas that they then went on to pursue and implement and use to solve problems, which were quite innovative and interesting at the time. But this was before there were any computers in the sense we understand now, and any computer science. With the understanding that you have from a computer science education, many of these ideas can be expressed in a different way in terms of those concepts and are quite natural in that way. And one of them comes up here. What I claim is what we're looking for is simply a compiler. That language wasn't quite present back then, but remember that a compiler takes a high-level language program and turns it into one in a lower-level language. But that's exactly what we want to do. our high-level language is C, our low-level language is Turing machines, and I want to compile my C programs down to Turing machines. So if I can write such a C to Turing machine compiler, I'm done, because then to get the Turing machine corresponding to P, I just run the compiler on P. Notice that this does not require any understanding of what the program does. Your compiler doesn't try to ask itself, when given a program to compile, what is this thing trying to do? It just goes instruction by instruction. It takes a particular instruction and translates it into a block of instructions in the lower level language, and so on. It's a kind of blind, localized process. So it's really, in that sense, a different paradigm. It's a very interesting paradigm, which we may underappreciate exactly because, well, we've seen so many compilers. Okay, but it's still the case that that first step might actually be pretty hard. We make it simple, or at least simpler, by breaking it up into smaller steps. Again, there we actually reflect and mimic how compilers are written in modern-day computer science. So what we're going to do is, we won't compile a C program directly to a Turing machine. We'll first compile it to an equivalent assembly program, then maybe to machine code, then to code on a random access machine, and then to Turing machines, but starting with ones that are a little more generous than ours, ones that have multiple tapes, then down to 2-tape machines, and finally down to a 1-tape machine. Why do it this way? Because we can break a complex problem into a bunch of simpler steps. Also because we can exploit what's known. I don't really have to tell you how to take a C program into assembly and machine code, because you know that's doable. It's already happening on your system. A random access machine is something that has some finite set of instructions and a bunch of registers and some auxiliary memory. It's quite similar to a machine code, and it's not hard to believe or see that you can compile down from machine code to RAMs. The more novel elements is compiling down to various types of Turing machines. So let's talk a little bit about that. One of the things that makes Turing machines difficult, the basic Turing machine we have, is its very stringent memory management. The memory is just one long tape. It's like one big array that you cannot even random access. You have to sequentially access step by step. And it's cumbersome to store stuff there and manipulate it. We can gain memory flexibility already by just going to a 2-tape Turing machine. On this machine, there are 2 tapes, and at least it's like having, 2 arrays, and you can look at them kind of simultaneously, and it becomes easier. And it becomes even easier if you have multiple tapes. For example, to go from a RAM program to a multi-tape Turing machine, you could give 1 tape for each, register of the RAM machine. Remember, a RAM machine has a finite number of registers, and a multi-tape Turing machine would thus have a finite number of tapes. Okay, so what we're going to do here is we'll look at it in a little more depth at one of these steps. And that step is going from 2-tape Turing machines into our type of 1-tape Turing machines. So to do this properly, we have to formally define our new model. I have to tell you exactly what a 2-tape Turing machine is in just as much mathematical rigor as we did for a 1-tape machine. So let's start with the sort of high-level picture. In a 2-tape Turing machine, just like a 1-tape one, there'll be a control, and that control will be in some current state, which we'll call Q. Instead of 1 tape, there are 2. Both of them are left terminated, but potentially infinite on the right. And this control will have 2 heads, one of them scanning the first tape, the other scanning the second. These 2 heads can move completely independently. The control can tell each head to move at any point just 1 step, but they don't have to be in the same direction. They can be in different directions. So in more detail, at any point, the machine is in some state Q, and its heads are scanning some squares, 1 square on this tape, 1 on this tape. Then there will be a move. In any one move, the machine will read both symbols, the symbol under the first tape head and the symbol under the second. As a function of both of those symbols taken together and of the current state, it will determine what to write. And what it writes will replace both this and this. There'll be two symbols to write. And it will then move each head independently. One could move left, one could move right, both could move left, whatever. And it will transition to another state. As usual, what dictates how it does this is the transition function that we write for any particular two-tape machine that we design. That transition function will take input the current state and these two symbols, decide what are these symbols, the state to transition to, and two directions in which to move. It's also sometimes convenient to shorten the description that we see in this picture into what's called a configuration. The configuration tells us exactly what's the same thing once we know the language. The way it works is that the content of the first tape is all the symbols to the left of the queue concatenated with the ones to the right. So you can check that they match up. As usual, Turing machine tape is filled with blanks to the right of the last thing that's actually written. That's implicit, so your blanks going all the way down there. The blanks don't appear here. It's understood that everything else is blank. Putting the Q here means the head is scanning the first symbol of this string, which is a 1. That is the head of the first tape. There's a corresponding configuration for the second tape, which puts the Q in a different position because the head there is scanning the 4th square rather than here the 5th square. Notice it's the same Q. You have one state in the control, not one per tape. Let's take that a little further. We're going to now give the mathematical formalization of a two-tape machine. The long and short of it is that it's almost the same as that of a one-tape machine. In more detail, you have again a 7-tuple. We call this a 2TM for brevity. There's a set of states which should have nothing in common with the tape alphabet gamma. There is an input alphabet which does not contain the blank symbol. A tape alphabet. Every element of the input alphabet is a member of the tape alphabet, and the blank is always a member of the tape alphabet. Most importantly, the transition function, and this is the only place we really see a change. It takes a state, but now it doesn't take one symbol, it takes two. These are the symbols under the two heads. It gives you a new state, and it gives you the symbol to write and movement left or right. But it does that twice. This is for the first tape, this is for the second tape. So it'll tell you, write this on the first tape, move this way. Write this potentially completely different thing on the second tape, move in this potentially completely different direction. Then as usual, there's a start state and an accept state and a reject state. The reject and accept states have to be distinct. All the states belong to the set of states Q, so the size of this set can be has to be at least 2. Again, I'll just emphasize that there isn't a state per tape. There's one state for the machine. Here we are formalizing configurations. So the configuration in actual syntax is a pair consisting of 2 strings, and they follow the conventions of the single tape machine. Here, the U1, V1, U2, V2 are strings possibly empty over the tape alphabet. Q is a state. And you read this as saying the content of the first tape is U1 concatenated with V1. The content of the second is U2 concatenated with V2. The current state is Q. And the position of Q here says the first tape head is scanning the first symbol of V1, and the second tape head is scanning this first symbol of V2. A configuration tells you everything you need to know once you also fix the description of the machine to go forward. Nothing about the history is needed. You can just start running right from there. So Hopefully, again, just as for one-tape machines, you can actually see from this how these things execute. But if that needs any more elaboration or detail, again, in our modern computer science perspective, a nice way to do it is I'll write pseudocode to simulate a two-tape machine, just as we did for one-tape machines. And I think this is the best way to intuitively understand what it's doing and the best way to actually think about it. So what I'm doing here is I'm saying, suppose I'm given a two-tape Turing machine, which has these components. How would I write a program that runs it? Well, I would just create an array that stores the contents of the tape. Since this is a two-tape machine, I'll have two arrays, one for each tape. I will have a variable to store the value of the current state. How do I represent where the heads are? They're simply indexes into the arrays. So integers I1 and I2. How do I start executing? Well, I have to execute on some input W. I initialize the state variable to the SAR state, copy the input W into the first positions of the first tape. That's just a convention. We always put the input on the first tape in the first positions, and here we've copied it symbol by symbol. I'll add a blank after that. It's kind of implicit that everything else is a blank, but just for good measure. And I'll set the head positions both to 1. This says that I'm currently scanning square number 1. And now we loop. We keep looping until the current state is either an accept or a reject. As long as it isn't, we execute this code, which runs the two-tape machine for one step. What happens in that one step? We are currently in state Q. And what are we scanning? What are the symbols on the heads? Whatever T1 contains at position I1 is what the first head is scanning. What T2 contains in position I2 is what the second head is scanning. Because remember, the arrays hold the tape contents. So applying this transition function to these, we'll say transition to state P, write this symbol on the first tape and move the head this way. Write this symbol on the second tape, move the head this way. So let's do those things. Writing the symbol just means replacing the array contents at position I1 by the corresponding symbol for tape 1. And exactly the same for tape 2. The pointer is I2 and you replace it with T2 of I2 with this new symbol, and we can update the state. That leaves us with moving the heads. Well, the head positions are just these integers. Moving right means doing a +1 to the integer, and moving left is doing a -1. That's all there is. So if the direction to move is left for the first tape head, I want to set I1 to be I1 -1, and otherwise, meaning it's right, to be +1. And exactly the same for the second tape head, where the direction told to move is D2. What is this max for? This is the little technicality that I'm not allowed to fall off the left end of the tape. What these machines do is that if they are in position 1, in other words, if I1 equals 1, and you ask them to move left, they'll just say, nope, sorry, I'm not moving. Okay, and this condition simply codifies that. Okay, this need not halt. You may never enter a state that's accept or reject. But if it does halt, I want to see what the machine outputs. By convention, the output will be on the first tape again, and we will discover it as everything preceding the first blank symbol. So here I will copy everything preceding the first blank symbol into Y, and that's the output. Okay, so again, the purpose of this is really just to understand what the machine does, and I think it's a convenient way to do it that you could actually, program up if you felt like it. So now we come to the heart of the matter, which is that I want to show that two-tape machines are no more powerful than one-tape machines. That means if I'm handed a two-tape machine, call it M, I'm given its full description in terms of the 7-tuple. I want to design a one-tape machine, call it M prime, by also giving its full description as a 7-tuple. that's functionally equivalent to m. So now we would probably step back and think, how can we possibly do something like this? It's a programming project. How do we accomplish that? Well, what are our challenges? This thing has 2 tapes and I have only 1. So somehow my limited memory has to store that of this richer memory. I have to find some way in 1 tape to capture, represent 2 tapes. Another problem is that the 1 tape machine is only 1 head, but somehow this 2 tape one is moving as a function of things happening under 2 heads. How am I going to keep track of that? Okay, so these are the challenges we'll have to approach. Okay, so let's start thinking about how we design this. We will have to say what is the set of states and all these other things. And the trick, or one of the important insights, has to do with the alphabet. So let's look back a little bit at that. Remember that these things have 2 alphabets. There's a tape alphabet sigma and a tape alphabet gamma and an input alphabet sigma. Over here, everything got a prime except sigma. That's not a typo. The reason that happened is that it's maintaining the input alphabet, but it's not going to maintain the tape alphabet. It's going to significantly expand that in a way that will allow it to represent 2 tapes on 1 tape. What we set our new tape alphabet to, remember we get to pick it because we're designing this machine, is that its elements are 4 tuples. They consist of 1 symbol from this tape alphabet, followed by a bit, another symbol from that same tape alphabet, followed by a bit. We'll talk a little bit more about what these sharp symbols are, but there are additional choices for what could go in the first and third positions of this tuple. Now normally we'd write a tuple as a, b, c, d, but I don't want to look at it like that. I want to look at it like this. So I want to write the first pair above and the second pair below. Why is that? Because this gives me the interpretation of what it's meant to be. Remember that this whole thing formally is 1 symbol. It's something that our Turing machine reads as a single object and will know how to manipulate. When this 1 symbol is present in a certain cell of this machine, I have a certain interpretation or desire for what it means. What it wants to mean is that the 2 tape machine has gamma 1 in its first tape in cell I and gamma 2 on its second tape in cell I. And so this is just how we're capturing 2 tapes in 1. We're just kind of writing them one above the other by expanding the alphabet. Okay, what are the bits for? Well, where the head is something I will have to, on the 1 tape machine, store in memory. So I do that via a bit. The bit is telling me the head is here or it isn't. If the bit is a 0, it's saying this square does not hold the head. And if the bit is a 1, it's saying it does. Okay. What is the sharp sign for? It's just to tell us when there's nothing more on the tape of the 2 tape machine. The blanks are not quite enough to do that. We'll want something a little more firm, which is going to be this. So let's see how this translation would work. Suppose my 2 tape machine had a configuration like this. It's in some state, which is not shown here. The first tape contains all this stuff, followed by blanks. The second tape, this stuff. Head number 1 scans square number 3 here. Head number 2 scans square number 5. Red means the contents of the square that's being scanned. Blue is the heads. I want to represent this somehow in my 1 tape machine. I will expect that my 1 tape machine tape looks like this. Remember, each cell stores this 4 tuple, and it's 1 single symbol from the point of view of my 1 tape machine. How do I get these 4 tuples? This 0, 0 translates to this 0, 0. So you just look at the picture here and you get whatever is here. These zeros say the head is not sitting on square 1 in either case. Square 2, 1 and 0 is the contents, 1 and 0 appear here. 2 zeros again because the heads are not over here. For number 3, contents are 1 and 1, so I get 1 and 1. But the head is sitting here, so the second thing here is a 1. The second tape head is not sitting here, so I still have a 0. Okay, and I keep going. This becomes a 1 and a 1 because the second tape head is here. This has a 0 in this position because no tape head is here, and the content is this and this. Reds, again, are kind of indicative of where interesting stuff is happening. I put the sharp sign to terminate over here. I still use a 0 here because the head is not in these positions. Notice that the second bit can be a 1 in exactly one position in each row here. So there's a 1 here. There is no other place where the second bit is 1, naturally, because the head is in one position on each tape. Similarly, for the second row, there's a 1 here and nowhere else. It's not the same place, but there's only 1, 1. Okay, so after quite a bit of work, we've somehow come to the point where this is how we'd like to represent this stuff over here. Still, we're kind of thinking about this as we're in the middle of this process. So we have to next think about evolution. What is this two-tape machine going to do? Well, it will take a step. One step of its transition function might say something like, look at what you're scanning, write a 0, and move left. So it'll do that. Simultaneously, since you're scanning a 1 here, also write a 0, but move right. It's just an example of one transition that this guy could take over here. We now want to make the corresponding transition happen on our single tape machine. Now we know how we want to represent these configurations. We already saw how we represented this. This one has a corresponding one. It's obtained in exactly the same way. These symbols go here, zeros accompany them because the heads are not there. Here the symbols are 1 and 0. The head is here, so we get a 1. The head is not here, so we get a 0 below that, and so on. The second head is over here, so there's a 1 here, so forth. So this Turing machine says, I need to go from this to this. But for my one tape machine, this is no simple task. It can't do this in one step of its transition function. It's going to take a whole bunch of steps, and it's convenient to think of that as a little subroutine called update. We have to describe update in terms of a state diagram, which is eventually the formal description of the transition function. But intuitively, it'll go something like this. First off, we've been neglecting a little bit the actual state queue of these machines. Where is that represented or stored? Well, this engine also has state. So its state space is capable of remembering the state of this machine, together with tons of other stuff. But as part of that, it will remember this. So now when we want to simulate this transition, what our subroutine will do is, it has to work over here. It'll make a pass across this whole tape. In that pass, let's assume it begins over here, it will pick up where the heads of this machine are. So it'll find these two red things, and it'll remember what is actually both under the head and where the heads are. And it'll just store that information inside its own state. Now, once it's come here and completed that, it will look up the transition function of this machine and figure out what it needs to write and how it needs to move the tapes. So it'll figure out, I need to change this to a 0, move left, change this to a 1, move right. And now it has to implement that over here. That will require a whole second pass. It'll go back across the whole tape, find this again, and do a little back and forth and change this to this and this to this, and similarly over here. So this is a fair amount of work, and even this is not completely trivial to go from this high-level description of an update function to actually writing down pseudocode or a table description of the corresponding transition function. I'll leave that for you as a kind of exercise which can help you better understand the feasibility and details of a claim like this. One way to make this more interesting is that you could think about writing a Turing machine simulator to do this. So you would actually write code that would take input a 2-tape machine and then show you how the 1-tape machine works. For example, last time we saw that there is code for internet Turing machine simulators out there. Okay, and I'm going to basically leave it at that, in the sense that I'm not going to give more details about how this happens. One final remark is that we can say something about running time, and it's worth noting that our 1-tape machine has a running time approximately quadratic in the running tape of the 2-tape machine. So there is a blow up, but it's not ridiculously big, it's not exponential. And this is something that we will refer to later.